All right, so this is covering chapter 4. We're going to do 4.1. This is a very important chapter that we're going to cover. We're talking about vectors and the use of vectors in physics, and we're going to be coming back to this chapter several times throughout the year. So it's a pretty important chapter to get a good grasp on. Um, so let's jump in. Come on, or not. All right, so you can see it's broken down into 4 sections. We're just going to cover the first one, vectors in physics. So a lot of times a quantity, and we've talked about these two terms before, scalar and vector quantities. So remember that a scalar quantity is just a quantity that is just a number. That's it, a number, and of course its unit. So some examples of scalar quantities are things like volume and time and temperature. But sometimes a scalar quantity doesn't give us a good enough description for a particular physical quantity. And so we need to have a direction as well as a quantity, as well as an amount. And so here's an example. So if we need to get to the library from wherever we are, and you ask for directions to the library, you're told that it's a kilometer away. Well, if you are right here and you're a kilometer away, that could be lots of different directions for where that library could be. If you're exactly 1 kilometer away, it could be over here, it could be here, 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 here. You don't know which one. So just having a number doesn't really help you. You need a direction to go with that. So if the direction of northwest is given, in addition to the 1 kilometer, then we can know the exact location or have a better idea of the location of the library. So remember that a quantity that is specified by both a length and a direction is called a vector. So if we go back to our previous slide, and we're here and we're told, okay, we're 1 kilometer away. But if we're told we're 1 kilometer northwest, so north would be going up and then west here, we would know a little better about where that library actually is, as opposed to just being told it's 1 kilometer away. So we need both a number and a direction. I still can't seem to move this up any further. Okay, never mind then. A quantity that is specified by both a length and direction is called a vector. The length of the vector is what we call its magnitude, which is just the number amount, and that represents the length. Vector quantities are represented with arrows. So what we're going to be doing in this section is we're going to be drawing a whole lot of arrows. The length of that arrow is proportional to the magnitude of the vector, and the direction of the arrow represents the direction of the vector. So if you say 1 kilometer northwest, then you're going to be going in that direction 1 kilometer, because that is north and west both. Okay. Well, I can't see what that says. There we go. As you ride in a van, this is just an example. As you ride in a van on a straight highway, the speedometer reads 45 kilometers per hour. What additional information is required to specify the van's velocity? Okay, so speed, we said, is from a long time back. Speed is a scalar quantity, which is just a number. In order for it to be velocity, we need a direction. So you would have to say 45 kilometers north or 45 kilometers south or northwest or whatever. So in order to have velocity, you need the direction as well. When you just say 45 kilometers per hour, that is just your speed. And the length of that vector would represent the 45 kilometers. But if we're doing 45 kilometers north, we would be going up, and the length of that would be proportional to our 45 kilometers per hour. All right, so here's a better diagram of what we're doing. So in the previous example, walking northwest 1 kilometer would get us to the library. So if we're here and we go 1 kilometer northwest, that will take us to the library. But as you can see on this little grid, that means we're going to be having to make some intersections. We're going to be going through some grass, some fields, some yards maybe. So there's a lot of obstacles if I'm going straight northwest. So what I'm probably going to do to avoid those obstacles is I'm going to go down the street to the west and then turn and go up to the north until I get to the library. That's just a more practical way of doing that when we're in a city with streets and that kind of thing. So when we do that, when we break this up, when we take this one vector, and we break it up into its westerly direction and its northerly direction, we say that we are breaking it up into its components. We resolve that displacement vector, this displacement. We resolve it by breaking it up into how far west, how far north. And so that gets us into what we call its components. We resolve it into its components or its parts. Okay. And those are always specified along very specific directions. So it's always going to be on the X and Y axis. So we'll take our vector and we'll split it up into the X axis and the Y axis. Okay, and that's how we resolve it. So how far to the left or right do we go? How far up or down do we go? And that's how we resolve that vector. So if we want to find out what the resultant is, we want to find out what that is, we are just going to use sine, cosine, and tangent and Pythagorean theorem to help us figure that out. Because we always resolve it into a right triangle for that reason. So if we're in a right triangle, like you see here, the cosine of that angle is going to be, I got to think about it, some old horse caught another horse. So opposite over hypotenuse is cosine. Cosine is adjacent, caught another horse. Sorry about that. So cosine is going to be the adjacent over the hypotenuse. Remember, the slanted part of a triangle is the hypotenuse. The side beside the angle is the adjacent. The side opposite the angle is the opposite. Okay, so to find the x direction, I would just take, so remember cosine of theta is equal to adjacent Rx over the hypotenuse R. So if I want to get Rx by itself, I just multiply both sides by R, and that's what I get. And if I'm looking for the y, I'm going to do sine. So remember, sine of theta is going to be Ry over R. So I can solve for Ry and get the equation to find the y component. So this would be the equation to find the y component, and this one would be the equation to find the x component. Okay. And if you've forgotten your trig functions, remember some old horse, that's sine, opposite over hypotenuse, caught another horse, that's cosine, adjacent over hypotenuse, taking oats away, that's tangent, is opposite over adjacent. So if we wanted to match these up real quick, I know we can't actually do this on this particular thing, but tangent would be opposite over adjacent. Cosine would be adjacent over hypotenuse. And sine would be opposite over hypotenuse. Okay, and there is another example. So a local ski resort, you take a rope, tow to the top of the bunny slope. Your displacement vector for this trip has a length of 90 meters, 190 meters, and points at an angle of 26 above the horizontal. During the ride to the top, how far have you gone? The horizontal direction and the vertical direction. All right, so if we draw out, and this is one of those problem-solving skills that we learned earlier, that if you sketch out the problem, it's going to help you solve it. So here's our bunny slope. So we're going up that bunny slope there. And in the x direction, we break it up into its components. That's the x direction and the y, so that I make a right triangle. This right triangle has an angle of 26 degrees. Okay. Then we then have to find what d and dx and dy are. Well, we know d is 190 meters because it tells us that. Displacement vector for this trip is 190 meters and points at an angle of 26 degrees. So now we need to find the resultant, or find the component in the x direction and the component in the y direction. So we're just going to plug in. And so dx is going to be whatever the resultant is times the cosine of theta. dy is going to be whatever the resultant is times the sine of theta. We're just going to put those in our calculator and work them out and get our answer for displacement. All right, so let's look at the follow-up. It says, if the angle of the chairlift is decreased, will the horizontal distance dx increase, decrease, or stay the same? Assume that the length of the lift remains the same. Find the dx for the angle equal to 15 degrees. Okay, so now our right triangle, instead of being 26 degrees, our right triangle is now 15 degrees. Our resultant is still 190, and we're looking for dx. Oops, that does not look like a d. There we go. So dx is going to be equal to whatever d is times adjacent over hypotenuse, which is cosine of 15. So that is going to be 190 times the cosine of 15, which, if we do the math on that, make sure you know how to use your calculator. So 15 cosine is 0.9659 times 190. And we have two significant figures, so that's going to be 180 meters. So will the distance dx increase, decrease, or stay the same? So if we go back to the previous slide, we see that it increased. So in the previous slide, it was 170. Now it is 180. The components of a vector may be converted into magnitude and direction of the vector. So the magnitude of the vector r in the figure is found using Pythagorean theorem. So what we're going to do now is just go backwards. So we were given the resultant and we break it up into its two components. Now what we're going to be doing is we're giving the two components, and you've got to use that to find the resultant. And remember that we do using Pythagorean theorem, that which in math class you see it as c squared equals a squared plus b squared. And if I want just c, I'm going to need to take the square root of that, which is going to be c equals the square root of a squared plus b squared. And that's the same thing as that. Okay. And we're told what each component is, and we are told the angle. And we're looking for the resultant. So we're going to plug in our two components, 200 and 300, square them, add them, and then take the square root, and that gives us 361. To find the angle, let's go back and look at the triangle again. To find the angle, we're looking for this angle that's 56. We're going to pretend like it doesn't say 56. This is the angle we're looking for. And so we're going to think, all right, what trig function do I have or can I use to figure that out? Well, I know what x is and I know what y is. So opposite over adjacent, I could use tangent. So if we do the second function of tangent of 115, what did I say that was? Never mind, I didn't say. So remember that the tangent is the opposite over adjacent. So that's 300 over 200. So the tangent of the angle would be 1 and 1 1/2. So the tangent, the second function tangent of 1 1/2 is my angle. So remember, it's just basic algebra, and what I have to remind people all the time with algebra is you are simply doing the opposite. So if the tangent of the angle is 3 over 2, then the opposite of tangent over that angle would be tangent to the -1. So in your calculator, when you put that in and you do tangent to the -1 power of 3/2, that's going to give me my angle. So in my calculator, I'm going to put in 3 divided by 2, which is 1.5, and I'm going to hit second function tangent, and that's going to give me my angle, which is 56.3 degrees. Okay. There we go. All right. Okay. So here's another example. You plan to cut a piece of plywood to make a skateboard ramp. The ramp will cover a horizontal distance of 1.33 meters and a vertical rise of 0.38 meters. What are the required length of the ramp and the angle the ramp makes with the horizontal? So we want to cut the ramp so that it goes a horizontal distance of 1.33 meters, and it has a vertical rise of 0.38 meters. So we need to know, if I'm going to have those dimensions, how long am I going to have to cut this board so that it meets those dimensions? So I'm going to use Pythagorean theorem and put in my x distance and my y distance, and that tells me how long it's going to have to be, 1.38 meters. And then to find the angle, I'm going to use second function tan. So, and you're always going to use inverse tangent or inverse cosine. If you're looking for an angle, you always have to use that inverse function, not just the tangent function, because you're doing the opposite of what's done. So we're going to take inverse tangent of the 0.380 divided by 1.33. Opposite over adjacent. And that gives us an angle of 15.9 degrees. All right, let's look at this conceptual example. Suppose that each component of vector A is tripled. Does the direction of the angle of the vector, does the direction angle of the vector increase, decrease, or stay the same? So this book has a lot of these kind of conceptual questions. And what you need to try and do with these each time is set up a proportion, which is what they're doing here. So this is normally, but then I want to triple it. So if each component is tripled, what is that going to do to the angle? Okay. Notice that the factor of 3 is in the numerator and the denominator. And since it's in both, it's going to be exactly the same because it cancels out. So it's going to be exactly the same. So there will be no change at all. The direction and the angle is going to stay exactly the same. All right. And I think that is going to do it. Yeah. I believe that does it for this first section. Yes, adding and subtracting vectors is section 2. So